Welcome to the Deep Dive. Today, we're really tearing into a fascinating stack of sources, all focused on what many experts are calling a huge shift in cardiovascular health. We're talking about the 2024 breakthroughs targeting atherosclerosis. And if you, or maybe someone you care about who's over 60 is aiming for genuinely healthy aging, well, this deep dive is absolutely crucial.
It really is. Atherosclerosis, people often call it the silent thief of vitality. For decades, we've mostly just been managing the symptoms. So our mission today really is to look beyond just management. We want to explore the revolutionary potential of three interconnected areas: gene therapies, advanced stem cell repair, and this incredibly precise nanomedicine. And the data we're seeing suggests these aren't just small steps forward. They seem to offer, the genuine potential for actually reversing the disease.
And the scale of this problem really demands something revolutionary, doesn't it? Atherosclerosis is that slow, sneaky process where plaques, collections of fatty stuff, cholesterol, inflammation, they build up, they basically turn your flexible arteries into these rigid, narrowed traps.
It's a massive global crisis. WHO statistics from just this year, 2024, pin it as a major cause in over 17 million deaths every year worldwide, usually through heart attacks and strokes that result from it. And for you, the listener, the day-to-day impact might feel, quieter, but still really debilitating. That constant crushing fatigue, maybe pain in your legs when you try to walk, or that sort of foggy thinking creeping in. These are all signs that restricted blood flow is basically starving your vital organs, like your brain and muscles, of the oxygen they need.
Yeah, and we all know about the conventional treatments, right? Mostly statins. They are pretty good at managing cholesterol levels, that's true. But they often mean taking a pill every single day, and they can come with side effects, like those persistent muscle aches a lot of people struggle with. So naturally, this drives the search for fixes that get to the root cause, maybe even permanent fixes. Okay, so let's try and unpack this. How exactly are these new therapies, the ones targeting the genetic glitches and that runaway inflammation, how are they actually rewriting the biological script for our aging arteries?
Well, we really had to start with the blueprint, the DNA itself. Gene therapy tries to tackle plaque not just by dealing with the lipids floating around, but by going after its genetic roots. What we've learned is that a major bottleneck, a real problem spot in clearing cholesterol, is the overproduction of a protein called PCSK9.
Okay, hang on, let's clarify that. PCSK9, why is this specific protein such a villain in the story?
Right. Think of it like this. Your liver cells have these things called LDL receptors on their surface. They act like little vacuum cleaners, sucking the harmful LDL cholesterol, the bad kind, out of your bloodstream. PCSK9's job. It's basically to destroy those vacuum cleaners. It finds the LDL receptors and tells the cell to get rid of them. So naturally, the more PCSK9 you have floating around, the fewer vacuum cleaners your liver cells have, and the more cholesterol just builds up in your blood, feeding those plaques.
Okay, that makes perfect sense. It explains the hoarding mechanism, how the cholesterol gets trapped. So gene therapy is basically trying to use tools to tell the cell, hey, stop making so much of this PCSK9 protein.
Exactly. We can use precision genetic editing tools like CRISPR-Cas9, although for delivery it's often viral vectors, things like adeno-associated viruses or AAVs that carry the fix-it instructions. They deliver a gene that essentially silences PCSK9 production. This PCSK9 silencing is the key breakthrough we're watching closely. Trials like Verve Therapeutics' VEVE-101 are right at the forefront.
That sounds incredibly promising, I have to say.
Yeah.
But genetic editing, that's permanent, right? If you permanently change a gene, what happens if there's some unforeseen consequence years later? Or maybe the targeting isn't absolutely perfect. That permanence does raise some big ethical and biological questions, doesn't it?
That is absolutely the critical question, and it's why researchers proceed with such extreme caution in these trials. The elegance, though, of the PCSK9 approach is that while the edit itself might be permanent, its function is very specific. It's just reducing the amount of a protein we already know is harmful in excess. And the early phase 1 human data, it's really quite remarkable. We're seeing LDL cholesterol drops in the range of 55 to 65%. And these drops seem to last for years after just a single intervention. The ultimate goal is a kind of functional cure, something that could eliminate the need for taking pills for decades. But of course, long-term safety monitoring is absolutely paramount.
And the speed of the results you mentioned is pretty stunning too. You said in mouse models, just one jab cut plaques in half simply by letting those cholesterol vacuums do their job better. But plaque isn't only about cholesterol, is it? It's also this fire of inflammation inside the artery wall. How does gene therapy deal with that heat?
Right, it tackles inflammation directly too, which is crucial. It tries to make the environment inside the artery less hostile, less inflamed. Researchers are using those same AAV vectors, but this time to shuttle in powerful anti-inflammatory genes. Specifically, a gene called IL-10. It's known for calming down immune responses. A 2024 review in PMC highlighted studies showing this targeted delivery significantly reduced the risk of plaque rupture by about 40% in rabbit studies. And that's critical because plaque rupture is the event that actually triggers most heart attacks and strokes. It calms down those volatile foam cells, the macrophages bloated with lipids.
Okay, so gene therapy is like rewriting the instruction manual. Then the next logical step seems to be sending in, well, nature's own repair crew to fix the physical damaged stem cells.
Absolutely. Yeah. Now we shift from fixing the blueprint to actual cellular regeneration. See, atherosclerosis doesn't just build up junk, it actively damages the inner lining of the artery, the endothelium. It leaves behind scar tissue and makes the artery stiff. Stem cells, they're these pluripotent powerhouses. That just means they have this amazing ability to transform and heal that damaged lining.
So what kinds of stem cells are we talking about here? What's being used to rebuild these artery walls?
Well, the ones most often trialed right now are mesenchymal stem cells, or MSCs. They can be harvested pretty easily from sources like umbilical cords or even body fat. But their real magic isn't just turning into new endothelial cells, it's their signaling power.
Yeah.
MSCs release these tiny messengers, little packets called exosomes. These exosomes engage in what's called paracrine signaling. Basically, they talk to nearby cells and dramatically slash local inflammation.
Okay, can you break down that signaling part a bit more? You said these exosomes polarize macrophages. What does that actually mean for the listener? Are we talking about, like, changing their job description?
That's a great way to put it. Precisely. Macrophages are immune cells, and normally they're helpful cleaners. But inside an established plaque, chronic inflammation turns them into these destructive M1 types. Think of them as vandals, actively chewing away at the vessel wall, making things worse. The exosomes released by the MSCs, they essentially hand these M1 macrophages a new job application. They coax them, or polarize them, into becoming M2 types, the healing cleanup artists. So instead of attacking, they start sweeping up debris, calming inflammation, and actually repairing the tissue.
That's a much clearer picture, turning a vandal into a cleanup artist using chemical instructions from the stem cells. Very neat.
And the results we're seeing really back this up. In those advanced mouse models, we use the ApoE mice, which get really bad, human-like plaques. Simple IV infusions of MSCs reduce the existing plaque size by a measurable 30%. And at the same time, they improve the overall immune balance in the system, boosting beneficial T-regulatory cells.
And then going beyond just using natural repair cells, you mentioned engineered versions, like ultimate cholesterol devourers.
Right, that leads us to exciting platforms like Repair Biotechnology's CDP platform. This is really sophisticated bioengineering. They start with induced pluripotent stem cells, iPSCs, which can become any cell type. They guide these iPSCs to become specialized macrophages. But then, they engineer these macrophages genetically to make them devour cholesterol roughly twice as fast as your body's natural ones.
Wow, okay. That sounds like a pretty radical intervention in introducing super eater cells into the bloodstream.
It definitely is.
Yeah.
But the preclinical data from 2024 looks really compelling. In mice fed a high-fat diet, a single dose of these engineered cells managed to halve the amount of lipid, the fatty stuff, within the plaques. And we connect this back to the bigger picture. The goal isn't just about having a stronger heart, right? By repairing the blood vessels systemically throughout the body, we're aiming for better oxygen flow everywhere. That translates to potentially better memory and cognitive function because the brain gets more oxygen, and improved circulation to your arms and legs, meaning stronger limbs and less pain when walking.
Right. So, okay, we fixed the blueprint with gene therapy. We've sent in the construction crew, the stem cells, maybe even supercharged ones. The final piece seems to be delivery, making sure everything gets exactly where it needs to go. And this is where nanomedicine enters the picture, you said. How is this so revolutionary?
Yeah, this precision delivery aspect. It's often called one of the biggest hurdles in modern medicine. Nanocarriers, these incredibly tiny particles, measured in nanometers, so billionths of a meter, they're solving this targeting problem specifically for plaque. You see, plaque and the inflammation around it create a unique environment. The blood vessels near the plaque become leaky, and the tissue itself gets sticky. Nanocarriers are cleverly designed to exploit these conditions. They naturally accumulate in these hot spots, concentrating whatever drug or therapeutic agent they're carrying right where it's needed most. Models suggest this can reduce side effects by potentially 50%, compared to just letting the drug circulate everywhere.
That sounds incredibly clever, targeting the disease's own signature. But these nanos are, as you said, infinitesimally small. How do we make sure they don't just get filtered out immediately by the liver or spleen before they even reach the plaque? That seems like a big challenge.
It absolutely is a technical hurdle, and the answer lies in smart design. One approach uses what are called pH-responsive nanos. These might be tiny bubbles of fat called liposomes or complex polymers like PLJPEG. They're engineered to be stable and kind of inert in normal blood pH, but active plaque creates a much more acidic environment. When the nanocarrier encounters this acidity, it triggers a change. Maybe the particle breaks down or releases its payload. This concentrates the therapy right there, sometimes 10 times higher than if the drug was just floating freely. For example, studies using nanos coated with hyaluronic acid showed they cut key inflammation markers, like IL-6, by 60% in rabbit models just by targeting that acidic zone.
Wow, so the inflammation itself acts like the key to unlock the medicine delivery. That's really elegant.
It really is. And then you have another strategy, what you might call the macrophage hunters. These nanos are designed to specifically target those problematic M1 macrophages. Sometimes they're cloaked in materials taken from red blood cell membranes, maybe with specific markers like CD47, which helps them evade the body's general immune surveillance, like a stealth coating. Once they get taken up by the M1 macrophages, they deliver a payload designed to reprogram them, pushing them towards that beneficial M2 healing state we talked about. This targeted reprogramming approach has reduced plaques by about 35% in mouse studies.
And we're also seeing these tiny particles doing double duty, right?
Yeah.
Acting for both diagnosis and therapy.
Exactly, that's the convergence happening. Researchers, for instance, at NUS and Singapore have developed things called coordination polymers. These are special nanoparticles that can actually be seen on an MRI scan, so they pinpoint exactly where the plaque is located. But at the same time, they're slowly releasing a powerful anti-inflammatory and anti-growth drug like rapamycin right into that plaque. And we're even seeing early phase 1 human trials now for things called GDCEO2 nanozymes. These act like tiny catalytic converters, scavenging the harmful reactive oxygen species, those oxidative fire starters that drive plaque growth, while also providing imaging contrast.
That's incredible. But the challenge must still be making sure these materials are safe, biocompatible, non-toxic in the long run, and preventing them from just clumping together, aggregation, which could make them useless or even dangerous.
That's the crucial final piece of the engineering puzzle, absolutely. You can't have them clumping up. Thankfully, material science in 2024 is making huge strides here. Researchers are using clever coatings, sometimes natural materials like chitosan, derived from shells. They keep the nanoparticles nicely separated and stable in the bloodstream until they reach their target site. Biocompatibility is always key.
Okay, this really brings us to the idea of synergy, doesn't it? The real power seems to lie not just in one approach, but in combining them, the gene therapy, the stem cells, the nano delivery, and also integrating all this high-tech stuff with fundamental lifestyle choices. How does this all work together?
Exactly. Knowledge is most powerful when it's applied holistically, right? The integrated approach is what really holds the promise for restoring vascular youth. We're seeing trial data now, where, for example, nanovectors are used to deliver the CRISPR gene editor directly to the stem cells before they're even injected into the body. This pre-treatment significantly boosts the stem cells' homing efficiency, their ability to find and stick to the damaged artery lining. We're talking a threefold increase in models.
So it's like we're making the repair crew not only smarter and better equipped for the job, but also giving them a high-tech GPS system to get to the construction site faster and more reliably.
That's a perfect analogy. And you see these compounding effects. For instance, using stem cells that have already been gene edited like MSCs, where PCSK9 has been silenced these clear plaques much more rapidly than standard MSCs, or combining nanoparticles directly with MSCs. These nano-MSC hybrids can very efficiently reprogram macrophages and have been shown to cut down artery calcification, that hardening process, by 40%. And those specialized CDP nanos from Repair Bio we mentioned, they often work by embedding these super macrophages that have already been gene fixed, leading to that dramatic halving of plaque lipids in just weeks.
It's truly remarkable synergy, and we absolutely have to underline how natural complements like diet can amplify these processes, especially for Hertz over 60. What specific, simple dietary tweaks have been shown to actually boost the effectiveness of these advanced therapies?
Yeah, the sources are quite clear on this. Nutrition really helps prepare the biological battlefield for these therapies to work optimally. Take omega-3 fatty acids, for example. Eating fatty fish like salmon maybe twice a week does more than just lower triglycerides. Those fatty acids seem to actively prime the stem cells for homing. They make the cell membranes more fluid, helping the stem cells better recognize and latch onto the damaged endothelial tissue.
That's a fantastic mechanistic link. Simple diet helping sophisticated cell therapy work better. What about inflammation fighters from food?
Well, green tea catechins, the antioxidants in green tea, maybe from drinking about 2 cups daily, have been shown in some studies to enhance the efficiency of gene uptake by cells. They seem to help stabilize cell walls. So theoretically, if you were undergoing gene therapy, regularly drinking green tea might make your cells slightly more receptive to those fix-its instructions. And that's on top of green tea's own potential to help lower LDL cholesterol by maybe 10%. We also see benefits from traditional foods. Garlic, specifically its compound allicin, especially potent in things like aged garlic extracts or vinegars, appears to boost the body's natural processes that mimic nanopenetration and cholesterol efflux. That's the process of getting cholesterol out of cells.
And what about fermented foods? We hear a lot about the gut microbiome these days.
Right. Fermented foods like kimchi, for example, support what's called the gut vessel axis. A healthier gut microbiome generally leads to lower systemic inflammation throughout the body. This creates a less hostile, more receptive environment for therapies like stem cells to do their repair work effectively once they're introduced. So the integrated approach really means supporting the high-tech solutions with fundamental, robust biological health through diet.
So, putting it all together, what does this really mean for you, the listener? This integrated approach sounds like it promises something far beyond just slowing the disease down. It's talking about actual restoration of vascular youth. By tackling the lipid chaos, the inflammation, and the artery stiffness all at once, and supporting it daily with smart food choices.
It means we're genuinely crossing a threshold. We're moving past just managing symptoms. We're looking at intervention data, trial data showing consistent plaque reversal in the range of 30 to 50% in many preclinical and some early clinical settings. This isn't just a number. It translates into drastically slashing the risk of heart attacks, strokes, and other major cardiovascular events. It means potentially granting years, maybe decades, of unburdened joy, physical independence, and freedom. The future of healthy aging is starting to look truly vital, physically connected, and hopefully free from the limitations that stiff, diseased arteries impose.
That is profoundly hopeful, really exciting stuff. But of course, we always include this critical reminder. Please, always consult your own doctor, your primary physician or specialist, before making any health decisions, especially if you have existing conditions. Our discussion here is for empowerment, for education, definitely not a prescription.
Absolutely. And if we just step back and look at the bigger picture here, what's really striking is how close we might be to a future where perhaps a single, highly targeted intervention, maybe an injection, maybe a localized infusion, could potentially reverse decades of accumulated damage in the arteries. It's like offering the entire cardiovascular system a genuine fresh start.
Okay, so here's a final provocative thought for you to mull over as you continue your journey towards vitality. We talked about using bits of red blood cell membranes to cloak nanoparticles, turning them into stealthy macrophage hunters. If we can engineer technology to essentially hide within your body's own systems like that, could the very next evolution be something even more integrated? Could we perhaps genetically program your own existing immune cells, your body's natural cleanup crew, to become the delivery system, fully merging the therapeutic machine with the host, eliminating the need for introducing external particles altogether? Just something to think about.